Hello and welcome to this video for Chemistry 30. In this video, we're going to talk about how to answer questions that ask you to order by strength oxidizing agents and or reducing agents. Okay, so questions can be very straightforward where you just use your data booklet. And we know the strongest oxidizing agent is on the top left, the strongest reducing agent's on the bottom right, and then based on that, we just follow the orders from the chart. But what if you have other data that is either artificial or fictional elements, and so you can't use your data booklet? Now, there's a couple of ways you could be given these questions. The first is by given a reaction chart like this, where you're given a list of metals and they're put into aqueous solutions of their ions. Now, when you have an ion and an atom, whether they're real or fictional elements, you need to figure out which form the ion forms or the atom forms are the OAs and which are the RAs, okay? Now, there's kind of a shortcut to figure this out. The one with the higher charge is the OA, okay? So, for example, copper has a charge of 2+, so it has a higher charge, or even oxidation number. Remember, we used that term already. It has a higher charge than copper as an atom because copper as an atom has an oxidation number or charge of 0. You could also write a reaction where it's gaining electrons, and the copper 2+ ions would need to gain electrons to form copper solid. So that means that this would need to be a reduction half reaction that my copper ions are going through. And when copper ions are being reduced, that means they're acting as an oxidizing agent. Okay? So the higher the oxidation number is the oxidizing agents, the lower oxidation number is the reducing agents. And the copper, zinc, lead, and silver as atoms all have an oxidation number of 0, whereas their ions are all 2+. Okay? So that's the first step, identifying which are the OAs and which are the RAs. Generally speaking, your metallic ions are always OAs because they're positive in charge, and their atom forms are the RAs. But when you have negative ions, it's backwards. Negative ions are actually like if you have a nonmetal or a negative ion, the ion is the RA and the atom is the OA. Okay, so you just have to, like I said, kind of be careful. You can write half reactions to see what half reaction they go to know if they're reacting as an OA or an RA. So in this chart now, given this data, we are given checks if a spontaneous reaction occurs and a line if there is no spontaneous reaction. So based on that, if we're asked to order these from strongest to weakest, or of course you could be asked to order them from weakest to strongest, you're basically looking at how many checks, how many spontaneous reactions does that species have. So let's look at the question. Put the oxidizing agents in order from strongest to weakest. So if I go back, my oxidizing agents again are the ions. The one that reacts the most is the silver. It reacts with everything except itself. Okay, so that means silver ions are the strongest oxidizing agent. Then copper ions, they react with two things, so they're the second strongest. Then the lead ions reacts with one thing, it's the third strongest. And then last is zinc because it's reacting with nothing, so it is the weakest. Okay, so from strongest to weakest, the oxidizing agents, from strongest oxidizing agent to weakest oxidizing agent, it would be silver 1+ aqueous, copper 2+ aqueous, lead 2+ aqueous, and zinc 2+ aqueous. Okay? Now for my reducing agents, the question on the next slide also wants the reducing agents from strongest to weakest. Okay? So my reducing agents now are the solid atom forms of our elements. Okay? So the one that reacts the most is zinc. Zinc reacts with 3 of the metals, obviously everything but itself. So that is my strongest, zinc solid. Then there's lead. Lead reacts with 2 things, so that would be the next strongest. Then we have copper. Copper reacts with 1 metal, So that's the third strongest, and leaving us with silver as the fourth strongest. Now, we did a lab, or normally I would do a lab with my Chem 30s when we first start this unit, where we actually do these reactions, mix these metals with their solutions to order their strengths. Okay, and you'll notice again when something is a strong oxidizing agent, in one form, its ion form, it is a weak reducing agent in its atom form. Okay, so these lists are opposite of each other. The stronger something is as an OA, the weaker it is as an RA, and vice versa. Okay, so if you're given sample lab data like this, all you're doing is checking for the number of reactions it has. The more reactions it has, the stronger it is. Okay, now what if instead we are given a question that looks like this? Okay, we're not mixing everything together and told whether or not it reacts. So this is a little more complicated. Okay, now what you're going to do for these questions is generate your own mini reduction table. And like you have in your data booklet. So the OAs are on the left-hand side. Sorry, my dogs are playing. The RAs are on the right-hand side. And we're going to use our spontaneity rule and, like a puzzle, place all of the species relative heights to each other based on if they're spontaneous. So if a reaction is spontaneous, that means your OA on the chart will need to be somewhere higher than the other substance as an RA. And if it's non-spontaneous, then the OA has to be lower than the RA on the chart. Okay, so it all has to do with relative heights, whether it's spontaneous or not. So if it's spontaneous, the OA is above the RA. If it's non-spontaneous, then the OA needs to be below the RA. Okay, so that's essentially what you're doing. Now I have a video here that I like to show that looks at this process. Okay, and I will post it in the link so that you can watch that if you would like. So I'll go through these examples and show you what we're doing. I have another slide here that gives us a little more space to work with. So the first thing you want to do again is identify which form of the elements are the OAs, which are the RAs. So again, the more positive or the higher oxidation number. So here my silver's oxidation number is 1, silver ion, and then here my copper metal is 0. So the higher charge is the oxidizing agent, the lower charge is the reducing agent. Okay? Remember, your oxidizing and reducing agents will always be the reactants, not the products. So my zinc ion in the next reaction is the OA, the silver metal is the RA. Copper ion in the next reaction is OA, zinc solid is the RA, and again silver ion is the OA, and mercury liquid is the RA. Again, to simplify, positive cations of metals are usually always OAs, and then their elemental form are RAs. So now, like I said, I am making a chart like you have in your data booklet, okay, where it lists reactions as reduction half reactions. So we have arrows, technically equilibrium arrows throughout the chart, right, for every half reaction, because you can read them in both ways. And so everything on the left-hand side is the oxidizing agent form, and on the right-hand side is the reducing agent form. Now I'm going to start with my first reaction. The fact that I'm given products versus another reaction where there's no products, if products are formed, that means this reaction is spontaneous. If it says there's no reaction, that means the reaction is non-spontaneous, okay? So we can also quickly identify the spontaneity of these rules based on the information we're given. Now, this is very important, again, because it's going to tell us the relative placement of these species. So, for example, reading my first reaction, my silver OA is spontaneous with copper as an RA. So that means, now where do I put my silver ion? First of all, it has to be on the left-hand side because it's an OA, but I don't know where to put it on the page, if it should be at the top or the bottom. So I'm just going to put it in the middle, okay? So starting my chart, there's my silver as an OA. And it is spontaneous with copper, so that means copper has to be lower down on the chart, okay? That's what the first reaction tells me. The fact that the silver ion is spontaneous with the copper metal, if the silver ion is the OA, it therefore has to be higher on the chart than the copper as the RA. Now I'm going to finish their half reactions just like the chart in the data booklet. My silver ion would gain 1 electron to form silver solid, and my copper would have been formed from copper ions gaining 2 electrons to make copper solid. Okay? So again, based on this first reaction, I knew the relative height of the silver OA must be higher than the copper as an RA because it was spontaneous, and that's what the spontaneity rules state. Okay? So there's relative heights of those two metals. Now I can look at my next reaction. I have silver solid as an Ra, which is already on my chart, and it is reacting with zinc ions as an OA, and it is non-spontaneous. So that means my zinc ions, which I'm going to put in red, need to be lower. They need to either be here or here. But they need to somewhere be lower than the silver because with silver as the Ra, it's non-spontaneous. And the non-spontaneous means the OA is lower than the Ra. Okay, so I don't know which spot it's in yet, so I'm not going to finish its half reaction. I'm going to go to the next reaction and see if it gives me information to figure this out, where the zinc should be. Okay, so in the next reaction, I'm told zinc solid with copper ions are spontaneous. So here is my copper ions already placed on the chart. We're not sure where the zinc should be yet, if it should be above or below. But we know that zinc solid as an Ra, when it reacts with copper ions, it is spontaneous. So that means my zinc needs to be lower. In order to be spontaneous with copper ions, the Ra has to be lower than the OA. Okay, I didn't mean to do that in purple. We're going to change that, not that it really matters. We're going to change that to red. So that means my zinc is that zinc ion, not up here. Okay, my zinc needs to be lower than my copper ion because my copper ion is spontaneous with zinc. Okay, and if I finish its half reaction plus 2 electrons, there is my chart, now having 3 metals relative heights to each other. Okay, last reaction, we have mercury as an Ra reacting with silver ions as an OA. My silver ions are on this chart. Mercury as an Ra is non-spontaneous with silver. So that means my Ra of mercury has to be higher than my silver. Okay? Because if the Ra is higher, it's non-spontaneous. So if my mercury is higher, and I finish mercury's reaction, mercury is multivalent, so I'm not 100% sure. I think it's the 2+ charge is the more common one. Now, of course, these questions are going to be found in a numerical response, multiple choice type of question. So you don't really have to worry too much about whether you know exactly what charge it has, because the numbers will be given to you. Like whether it has a 2+ or a 1+, it'll be given to you. Okay, now let me just go back through these reactions and show you again how this worked. Okay, so again, my silver OA is spontaneous with copper as an Ra. So my silver OA must be higher than copper as an Ra. Okay, that's what the spontaneity rule states. So my copper is lower than my silver. In the next reaction, we're told silver metal as an Ra, which is here on the chart, is non-spontaneous with zinc as an OA. So that means my OA of zinc has to be lower based on the non-spontaneity rule. In order to be non-spontaneous, the OA has to be lower than the RA. Okay? If we look at the next reaction, my zinc RA, which is right here, has to be higher, or sorry, the zinc has to be lower than the copper. The copper has to be higher, the copper ion, OA, because copper with zinc is spontaneous. Copper ions with zinc solid are spontaneous. So the copper ions have to be higher than the zinc metal. And then lastly, mercury as my RA is non-spontaneous with silver as my OA. So my silver ions, OA, have to be lower than the mercury. Okay, so after you place everything, do a check like that. Make sure everything is placed relative where it needs to be based on the spontaneity rule. Okay, so this all has to do with the spontaneity rule of OA being higher than RA and vice versa. Now, I know at the top left is my SOA, and as I go down, they get weaker. And on the bottom right is my SRA, and as I go up, those get weaker. Okay? Reads the questions very carefully. It wants the oxidizing agents in order from weakest to strongest. So my oxidizing agents from weakest to strongest would actually be the ones on the left at the bottom going up. So zinc, copper, silver, mercury. Okay? And then the reducing agents from weakest to strongest would be on the right-hand side, the metals, from the top down. So mercury, silver, copper, and then zinc. Okay? So once you have your chart complete, it's just like the data booklet where the SOA is at the top, the SRA is at the bottom. You just follow what the question's asking if it wants weakest to strongest or strongest to weakest. Remember, the OAs again are on the left, the RAs again are on the right. Okay, let's look at another example. Now, this example has negatively charged ions. When you have anions or negatively charged ions, the anions are actually the RA, and the elemental form are the OAs. Okay? Because again, the higher oxidation number, the elemental forms are 0, the ions are negative. The higher oxidation number are the OAs. Okay? So my ions are now RAs, my atoms are OAs. And you'll see 2's here because these elements are diatomic. So now again, when I generate my mini reduction table, my OAs must be on the left, my RAs must be on the right. Now my first reaction says Y2 as the OA, so I'm going to put Y2 in the middle of the page on the OA side, and it is reacting spontaneously with X, okay, the RA. So that means that my X, and there's 2 of them just to balance the reaction since they're diatomic, they must be lower than my OA because the reaction was spontaneous. So to be spontaneous, my OA must be higher than my RA. Okay? Now I can complete these half reactions. The Y2 would gain 2 electrons to make 2 Y ions. And the X2 would have gained 2 electrons to make the 2 X ions. Okay? These are like the halogens, diatomic, fictional elements. Okay, next reaction. I'm told Y2, which is already on my chart, is non-spontaneous with the RAZ. So this means my Z has to be higher. Right? My spontaneity rule states if it's non-spontaneous, the RA must be higher than the OA. So once I've placed my Z higher, I can finish Z's half reaction. And now I have 3 metals placed on the chart. I look at my next reaction, and my next reaction tells me Z ions, Ra, which are already on the chart, are spontaneous with W as an OA. So in order for W as an OA to be spontaneous with Z as a Ra, it must be higher. The OA is always higher than the Ra if it's spontaneous. So the W must be higher, and if I finish its half reaction, I now have all of my metals placed in order of tendency to react. Okay? So again, if we want to do a check to make sure we've done this correctly, my Y2OA, here's my Y2OA on the chart, is spontaneous with X. Here's my X ions. And that looks good, right? In order to be spontaneous, the OA is higher than the Ra. So that looks good. Then I have my Y2, which is here, being non-spontaneous with Z as the Ra. And so again, in order to be non-spontaneous, the Ra is above the OA. So that also looks good. Okay? Then we have W with my Z. That reaction is spontaneous, which looks good. If it's spontaneous, the W should be higher than the RAZ. Okay? So there, everything looks in proper order. Now, again, my SOA is at the top on the left-hand side. My SRA is on the bottom on the right-hand side. And now I follow their lists on the chart. It wants the oxidizing agents from strongest to weakest. So from the top down in this case. And it wants my reducing agents from strongest to weakest. So from the bottom up on the right-hand side. So our oxidizing agents would be W2, Z2, Y2, X2. And my reducing agents from strongest to weakest would be X ion, Y ion, Z ion, and W ion. Now again, there's no balancing coefficient in front of these because you're just identifying the ions, not how many there are, just what they are. So that's why there's no 2's in front of them. Okay? I believe, there's one diploma question. And then that's it for this lesson. So again, we have positive ions, back to positive ions. So the positive ions are the OAs, and the atom forms are the RAs. Okay? Now, the question wants the oxidizing agents above from strongest to weakest. So right away, I can actually cross out C and D because those are reducing agents. The oxidizing agents are the ions, okay? And if I start a chart for myself with my OAs on the left and my RAs on the right, I start with my H. I have 2 H's just because it's diatomic. As my OA being non-spontaneous with PT. So PT must be higher than H to be non-spontaneous, okay? So if I finish PT's reaction, PT would be gaining 2 electrons to make PT solid. Hydrogen also gains 2 electrons to make H2 gas, okay? Next, we have nickel and Ce. Neither of those are on there, so I can't look at those yet. If I look at the third reaction, I have hydrogen ions and nickel, okay? Hydrogen ions are making products, so they are spontaneous with nickel, which means nickel needs to be lower, right? My OA must be higher than my RA. So my nickel ions will gain 2 electrons to make nickel solid. Now I can go back to this reaction here. I have nickel ions on the chart now, and cerium needs to be lower because cerium as the Ra is spontaneous with nickel as the OA. So it has to be lower than the nickel. And cerium actually has a 3+ charge, so it gains 3 electrons. Okay, so now like it said, it wanted the OAs, these are my OAs, from strongest to weakest. So strongest is on the top, and then as we go down, they get weaker. So the answer would be A. Okay, hopefully that lesson made sense. It's kind of like I said, a puzzle. You're placing these species together based on the spontaneity rule, making your own reduction table. If it's spontaneous, the OA must be higher than the RA. If it's non-spontaneous, the RA must be higher than the OA. Thank you for watching this video.